21.4. Now, these chapters, sections on the chemistry of specific carboxylic acid derivatives, I'm going to illustrate in this sort of explosion chart manner that I have illustrated here on my left. But before I do that, for the acid halides, and we talked about the chloride, but the bromide can also be made, and it's accessible. It's actually a little more reactive than the chloride. So we can take a carboxylic acid, we can react that with PBr3. Now we've seen the reaction with PBr3 with alcohols before, and it's a similar type thing. One of the bromides gets displaced. I'm not going to go into the details here, but that gives a mixed phosphorus carboxylic acid anhydride that of course is more reactive and then produces the bromide. Look at some specific examples of that on your own. Now I want to touch on the mechanism of all of these substitution reactions I'm about to talk about. And they're all very similar. So I'm going to take one, the reaction with formate, and I'm just going to take the simplest pieces to work with. So as we've already seen, nucleophilic acyl substitution occurs by an addition to form a tetrahedral intermediate and then an elimination. So we have the addition. This is a reversible process. It produces a tetrahedral intermediate. Of course, this tetrahedral intermediate has two leaving groups. If you kick out the formate, you go back to where we started from. But to go forward, you bring the lone pair down, you displace the chloride leaving group. This is reversible, but in this case, this one's going to lie heavily toward the anhydride. And so there you have the fundamental mechanism. And then all of these work essentially that way. Some form of the nucleophile attacks the carbonyl. You have a tetrahedral intermediate that then has a leaving group that leaves. And in these cases, the chloride and the bromide are the leaving groups. So let's look at some of these reactions now. And since I started with the formation of an anhydride, I will, coming back now to look at the specific reactions, we're going to start with the formation of the anhydride, which we just looked briefly at the mechanism. Of course, we're looking at the reaction of the acid chloride here in the center. If it reacts with water, it hydrolyzes back to the carboxylic acid. Now, if we replace one of the protons with an alkyl group, that's an alcohol, we'll need a tertiary amine base. In this case, I have pyridine in there, and we can make esters very readily in this way. It's probably the most common way of making esters. Of course, you have this side product here of the pyridinium hydrochloride, the proton coming from here, and the chloride coming from the acyl chloride. Now, the reaction with amines we need to pay special attention to, because an amine is itself a base. And so we typically will have to use two equivalents of an amine base. If it's a simple one like dimethylamine, that's fine, we don't care. We produce the dimethylamide product. But as the amine gets more complicated, you don't want to waste half of it, because of course the other product here is the ammonium chloride. So we can put in a cheap base like sodium hydroxide. Inexpensive, produces water, it's no problem. Amides are stable to simple aqueous conditions. Again, remember our skin, we don't dissolve when we jump in the swimming pool in the summertime. These can be reduced. When they're reduced, they go all the way to the alcohol. You can't stop them basically from going to the alcohol. And the two hydrogens on the carbons come from the hydride. You can also add nucleophiles. This is a very electrophilic center. And if you add a Grignard reagent to it, notice it adds twice. Again, you cannot stop with one addition. The ketone that would be the immediate product is too reactive. Now, there is a way to produce ketones from acid chlorides, and it comes from using Gilman reagents. These are the cuprates, dimethyl lithium cuprate here. We'll add and displace the chloride. Again, that methyl carbon bond is not nearly so, methyl copper bond. This is a copper, methyl cuprate, is so basic, is not so basic as the Grignard reaction. So it's pretty straightforward then, and these give high yields of the ketones, and that's a very useful thing. So these sections on the specific functional groups, this is my preferred way of presenting them. So